Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 98 of this seminar. Today we have two excellent speakers, Praveen Agarwal and Neste. Introducing Praveen Agarwal, we have to Professor Mauricio Sepúlveda. Thank you, Mauricio. You can start,
Okay,
please.
thank you. Thank you very much, Juan. It's a great pleasure for me to present the following talking about the Professor Praveen Agarwal. He comes from the Anand International College of Engineering from India, and he have a lot of he's author of a lot of paper and books, and manage and editor of some books and several papers. And today he talk about extended Caputo type fractional derivative operator. Please, Professor Praveen, you can start.
Yeah, very good morning, everyone, and everybody. I say good evening from the India, because here is starting the midnight. So it's a really pleasure, and I am very happy to share my research via this platform. So I am thankful to the organizing committee of the EDP and the Applied Mathematics Seminar organizers to invite me and give me opportunity to share my research via this platform. So today I am going to present a talk on the extended Caputo K-type fractional derivative operator. So in this particular talk, we discuss about the abstract of my talk is some fractional integral and derivative operators of any arbitrary order have gained considerable popularity and importance during the past few decades. Friends, as we know that in these days, when we are dealing with the artificial intelligence and machine learning, then some of my colleagues from the United States, United Kingdom, and as well as from the Turkey, we are also using the fractional calculus operator in the machine learnings and the artificial intelligence. And yes, so we are very happy we got the some connections and to find out the some competitive results. So that is why the fractional calculus is very important in these days. Now, if we are talking about the Caputo fractional derivative operator is a very important and most popular fractional operator in the field of the fractional calculus. In this talk, we present some extensions of K hypergeometric functions and develop the extended Caputo K-type fractional derivative operators by using the two parameters K Mittag-Leffler functions. So here I mention that the K Mittag-Leffler function, basically it is a family member of the spatial functions, because we are dealing with the many spatial functions, like if I am saying the elementary spatial function is a trigonometric function, exponential functions. So on the similar lines, the Mittag-Leffler function is a very important family members. Okay, and then we can introduce the K Mittag-Leffler function for our study, because we have discussed about the extended Caputo K-type fractional integral operator. So my objective at here, first of all, we have giving the some basic definitions, classical definitions, and then we discuss about how we can extend the spatial functions, especially the K Mittag-Leffler functions, or the some functions which is required for the extensions of the K Mittag-Leffler functions. And after that, we have discussed how we can extend the classical Caputo fractional derivative operators in the form of the extended Caputo K-type fractional derivative operator. In this talk, if I am talking about my keywords, so we have taking the keywords is given by the K gamma function, then K beta function, Then we have the K Pachamber symbol, K hypergeometry function, Mellin transform, Caputo K fractional derivative operator. So let's begin with the development of the how we can develop this particular area. So if I am talking about the starting phase of the development, then I am taking the some of the introduction and preliminary results of the particular direction. So some fractional integral and derivative operator of any arbitrary order have gained considerable popularity and importance during the past few decades due to the application point of view. The Caputo fractional derivative operator is one of the most powerful of them, which provides an important formula for fractional derivative. It also allows traditional initial and boundary conditions to be included in the formulations of the problem, and its derivation of a constant is 0. Also, it is a customary in groundwater investigations to choose a point on the center line of a pumped borers as a reference for observations, and therefore neither the drawdown nor its derivative will vanish at the origin, as we mentioned in the reference number 3. In such situations where the distributions of the piezometric head in the aquifers is decreasing the functions of the distance from the boreholes. So the problem may be circumstanced by the rather using the complementary or Weyl fractional order derivatives. So my meaning is that the fractional calculus is having the multiple operators, and out of them the Caputo fractional derivative is showing its important many times. So that is why, due to its compositions of the function, so it is a very, very important fractional operator. On the same time, the spatial functions and fractional operators are two major areas of the research in which a variety of refinements and generalizations are currently available. So here I'm talking of one of the research group, which is working with my PhD research scholar, which is Lakshmi Parikh, have studied some well-known the K-type gamma functions, beta functions, and the hypergeometry functions, discuss many important results and theorems in the reference number 10 and 11, which are recently published in the Applied Mathematics and Computations and the IEEE. So I am talking about the first definition, the K-type gamma and beta functions, which is a joint work of me and my team, which is already published. And we are giving the equation number 1. You can see at there, the equation 1, the left-hand side is represent the extended K-type gamma function. And the right-hand side is giving the definitions of in the form of the integral, which is a 0 to infinity t raised to power nu minus 1, and it is a K Mittag-Leffler function, which is having the parameters with the terms of the dt. And the extended K beta function is represented by the equation number 2. And for the convergence of the equation 1 and 2, the K is greater than 0, and minimum real part of nu1, nu2 should be greater than 0. The parameter s is greater than equal to 0, and a real part of s1, s2 should be greater than 0. Now, we're talking about one of the very important result which is required over study, the K-type Gauss hypergeometric and confluent hypergeometry function, which is also introduced by me and the group of my PhD students by the Lakshmi Parikh. So it is already published, and in which we have mentioned the K-type Gauss hypergeometry function by the equation number 3, which is given by the composition of the term of the extended K beta function and the K beta function. This is the combination of these two functions. And on the same time, the equation number 4 is represent the K-type confluent hypergeometry function, which is given by the equation number 4, which is also combination of the extended k beta function, which is given by the equation number 2. You can see it here. This is the equation number 2 and the extended k beta function, and the equation 3 and 4, the formula 3 and 4 are convergence, but the k is greater than 0, and real part of the nu1, nu2 should be greater than 0, real part of nu3 is greater than 0, and real part of s1, s2 greater than 0, mod of w is less than 1 by k, and extended beta function is the extended k beta type function. So to get our result, we need to define the k Mittag-Leffler function. So for my study, I have introduced the k Mittag-Leffler function, which is given by the Nisar and his group in the equation number 5 and 6. Here I am giving some information about the initially extended k Mittag-Leffler function, which is given by the Nisar and his group, which is given by the equation number 5 and equation number 6. Now we come to our main result. So here you can see that in our main result, we introduce the extensions of the k hypergeometry function, the Appel's k hypergeometry functions, which we can say that in the f of f1k and symbolically f2 of k. So now my first definition is coming in definition number 2.4. The extended k hypergeometry function is defined by the equation number 7, and we can symbolically represent by the k of f of s1, s2, k of s, p1k, p2k, p3k, w. The right hand side of the definition comes in the summation formula, which is having the formula of the summation n equal to 0 to infinity, and we are going to the combination of the extended k beta function. There is a extended beta function, and on the same time this is a k beta function. The definition 7 is convergence for the given conditions, which is given at here. So these are the convergence condition. For that, the equation number 7 is our exist. Now we are giving the another definition number 2.2, which is called the definition of the extended Appel's k hypergeometry function, which is represented by the f of 1k, which is defined by the f of s1, s2, 1ks, and the right hand side is given in the term of the summation formula. So you can see it here in the summation formula. It is a combination of the extended k beta type function, and it is the extended k beta function, and the definition 8 is convergence for these given conditions. So it is a convergence for these given conditions. On the same time, we require to establish our result. We require the another definition, which is called the extended Appel's k hypergeometric function f of 2k, which is represented by the equation number 9, and you can see at here the equation number 9 is having the left hand side, which is given by the f of s1, s2, 2 of ks, and the right hand side is a combination of the summation formula, which is having the extended k type beta functions and then the k product of the two extended k beta function at here, and in the denominator we have the two another product of the k beta extended k beta function. So the equation number 9, the definition 9 is a convergence for these given conditions, which is given at here. Now we are coming of the first of all, we have proved the some of the fundamental results for all the three new definitions. So we are giving for the first theorem. So this is the theorem for all the three definitions. The following integral representations are valid for the extended k beta function, extended hypergeometry functions, and extended Appel function, and which is given by these three definition, which we have mentioned at here in definition number 2.1, 2.2, and 2.3. So my meaning is that we have proved the sum of the fundamental result in the form of the theorem for the extended K hypergeometry function, Apple's K hypergeometry functions of the F1 type, and extended Apple's K hypergeometry functions of F2K type in the theorem number 2.1. So here you can see that we have proved the three results. This is the first result, this is the another result, and the third result. In the three results, we have represent all the definitions in the form of the integrals. So here I am using the represent the extended K hypergeometry function in form of the integral, which is having the kernel of the Mittag-Leffler function, which is introduced by the Nisar, and the involving the our definition, which is an extended hypergeometry function. And if we are talking about the second definition, which is a Apple's type hypergeometry function, which have the integral of the 0 to 1, and in the kernel we have the Mittag-Leffler function, and as well as the function with the definition of the Apple's F1K type. At the same time, if we are seeing the another definition, another result, which is having the extended Apple's F of 2K type function. So it has the double integral between the 0 to 1, which is having the kernel of the 2 Mittag-Leffler function, which is introduced by the Nisar group, and involving the definition of our extended Apple's F of 2K type functions. So these all three results, integrals are convergent, or we can say that the exist for the given conditions. And here I am giving the small brief outlines of the proof. By using the definition of the 7, we have write down the extended hypergeometry function, which is represented by this equation, and using the properties of the K beta function and the definition of the extended beta function, which is given by the equation number 2, we have this particular combination of these particular result. Because what we did, we have basically elaborate this beta function in the term of the we can say that we have elaborate this function in the term of the integral. So that is why we have the resulting term in this form. And by interchanging the order of summation and integration in the above as convergence, uniform, and the apply the 7, we get this resulting term, which is given by these below integrals. And after that, we have do some small computation at here by using some integral property, and using the definition number 8, we have the another result. On the same time, we are using the similar procedure, and we have proved the last result. So my meaning is that this we have used the basic definitions, and then we have compute all the results to integrate the to find out the final results of our main theorem 2.1. So here I am skipping some of the details for the time limit. So with the help of this computation, we have proved these three results. Now we come to our main result, because our main objective to develop the extended Caputo K-type fractional derivative operator. As by the equation number 11, we know that the classical definition of the Caputo fractional derivative, which is given by the equation number 11, and which is a give convergence for the real part of nu is greater than the r minus 1 is less than r, and n is belong to the capital N. The extended Caputo fractional derivative, which is defined by one of the research group from the Turkey, which they are giving by the equation number 12. Now, in case s equal to 0, the extended Caputo fractional derivative reduced to the classical fractional derivative operator. My meaning is that if in the equation number 12, if we put the s equal to 0, and after the little some computation, we got the classical Caputo definition by this form. After that, motivated by this concept, the Caputo K-type fractional derivative operator, which is defined by by the research group of my team, by the Lakshmi Parikh. They have introduced the Caputo K-type fractional derivative, which is given by the equation number 13. Here, inspired and motivated by the above all generalizations and extensions of the Caputo K-type fractional derivative, we introduce the extended Caputo K-type fractional derivative operator by using the two-parametric Metaglefer function. So here, we are giving the new definition, which is given by the definition number 3.1, and we have a represent our new result, which is in the term of the extended K-type fractional derivative operator, which is defined by the equation number 14. So you can see that we have the beautiful result, which is given by the equation number 14, which have the combination of the classical, which is having the extensions of the our function, which is called the two-parametric Metaglefer function. This is the two-parametric Metaglefer function, which is involved in the kernel, and we have developed this particular extension form of the Caputo fractional derivative operator, and this definition is true for the convergence conditions where k is greater than 0, real part of s is greater than 0, real part of s1 is greater than 0, real part of s2 is greater than 0, and real part of nu is greater than r minus 1 and less than r, and n is belong to the n. Here I mentioned very important remark. If s2 equal to 1, then we get the another type of Caputo K-type fraction derivative operator, which is defined by the definition number 3.2. At here, we have defined the another kind of fractional derivative operator, which we call the special case of the definition 3.1, which is converged for the given conditions. On the same time, we mentioned that in the case of the S1, S2 equal to 1, S equal to 0, and K equal to 1, the extended Caputo K-type fractional derivative operator reduced to the after the some computation in the classical Caputo fraction derivative. That is why our definitions are having the more important and more realistic. Now we have the giving the one of the theorem. So here I mentioned the theorem number 1, what it is saying for the extended Caputo K fractional derivative operator. If we can say that the let k is greater than 0, real part of s is greater than 0, and real part of s1 is greater than 0, s2 is greater than 0, and real part of nu is greater than r minus 1 to less than r, then this particular result holds true, which is given by the equation number 16. So here, due to the time limit, I am not giving the proof of this result. So this is the first result which we have represent in the form of the theorem number 3.1. Now, for our extended K-type Caputo fraction derivative operator, we have giving the another definition result, which is in the include in the theorem 3.2. Let a real part of nu is greater than 0, and we assume that that the function f of x is analytic at the origin with its Maclaurin's series expansion given by the f of x equal to summation n equal to 0 to infinity a n x to power n, where mod of x is less than rho for sum and belongs to the R plus, then the extended Caputo K-type Caputo fractional derivative operator is hold this result, which is having the extended Caputo K fractional derivative operator equal to extended Caputo fractional derivative operator involving the function is n equal to 0 to infinity summation a n x to power n, and this result holds true for the convergence conditions k is greater than 0, real part of s is greater than 0, and real part of s1 s2 is greater than 0. But due to the we have proved this result very easily after the using the some steps. So here I am skipping the steps and I am going to the another result. So here in the theorem number 3.2, 3, we have giving the one more very important result for the our extended Caputo K fractional derivative operator. The result is saying that let f of x is the analytical function on the disk mod of x is less than rho and has a power series expansion given by the f of x equal to summation n equal to 0 to infinity a n x is to power n. Then this result is holds true for the our extended K Caputo fractional derivative operator. Now we have discussed about the one more very interesting result, which is a very important result for the application point of view. So this is given by the theorem 3.4. Let K is greater than 0, real part of S is greater than 0, and real part of S1, S2 is greater than 0. Then there exists one of the very important result, which is involving our extended K type Caputo fractional derivative operator, which is having the two kind of variable, which is very, very important. Here I mentioned that now it has a two variable function. So now if in the kernel of the extended K Caputo fractional derivative operator having the more than two variable, then we are dealing this operator very easily and find out the composition formula, which is given by the right hand side. This is the composition formula, or we can say that the image of the left hand side. So we are easily find out this composition formula, and it is a converse for the above conditions, including the mod of K is less than 1 by K. So it shows that our extended K type Caputo fractional derivative operator is easily operate on the one variable as well as the two variable. On the same time, I am giving the one more definition for the three variable, which is given by the result number theorem number 3.5. Here you can see that this is the three variable functions which is involving in our extended K type Caputo fractional derivative operator. So that is why we are very confident now we can operate this one for the multiple results, right? So that is why our extended K type fractional derivative operator is very, very important for application point of view. And in our result, in our study, we have also present the sum of the generating functions for our extended K type hypergeometry functions, which we have studied in the definition number of the 3.1, which 2.1, which you remember. So we have developed the sum of the generating relation, which is given by the theorem number 4.4. And on the same time, we have developed another generating relation for the definition 2.2 for which is given by the theorem number 4.2, and one more generating results. So now we are giving the sum of the more results for our extended K type Caputo fractional derivative operator. Here I am using in the function is exponential function and operate over function, and we got the image formula very easily. So it is a create the utility or applicability of our fractional operator for all kind of the functions. Okay, so now I am going to conclude my study. The conclusion of my study is saying that in this work, by using the two-parametric Mittag-Leffler function, establish the extended Caputo K-type fractional derivative operator, generating function, and Malin transform of the new extended Caputo K-type fractional derivative operator are presented in our this talk. Here, it is important to mention that the presented extended Caputo K-type fractional derivative operator is very useful when dealing with real world problems, because it allows the traditional initial and boundary conditions to be included in the formulation of the problem. As we saw that in the sum of the results, which I have just shown you during my presentation. So in the extended K-type Caputo fractional derivative operator, we have find out the composition formula for the single variable, double variable, triple variable and usually we after that we have used the composition formula for the exponential function. So it shows that we are easily operate our operator on the multivariable problems as well as the different kind of the functions which are having the exponential functions, trigonometric functions, or the product of the two or more variables. So that is why for the application point of view, our operator is a more suitable to deal with the real world problems, because it allows traditional and initial boundary conditions to be included in the formulation of the problem. And in addition, the derivative of a constant is 0. Now we can conclude here by observing that the extended Caputo K-type fractional derivative operator examined here is a useful and has to be used according to the support of the function in our future work. Here I mentioned that recently in the beginning of my talk, I have mentioned that some of my colleagues, they are working in this direction, and as well as they are also using the artificial intelligence. So in these days, we are trying out use the artificial intelligence and the connection of the fractional operators. And in this part, our extended K-type Caputo fractional derivative operator is played a very important role, because recently we find out some of the very beautiful results for the image processing with the help of the machine learning and the K-type with the help of my extended Caputo K-type fractional derivative operator. Now, here I mentioned some of the references which I have used during the study of this particular work. Here I mentioned the very important result, which is given by the classical definition of the Caputo, M. Caputo in 1967. And on the same, after the definition of the K. Caputo, then many workers are using the generalizations and utility of this function. On the same time, me and one of the Italian group is working on, we have developed the new class of the hypergeometry function. On the same time, many researchers have developed the different kind of the results, which you can see at here. And here I mentioned the two very important results. So both are the published. I'm sorry, I have not mentioned their publication detail at here. So this is the one result which is published in the Applied Mathematics Computation. And this is the second one, which is published in the IEEE with the help with my research group. So these two results we have used in this particular presentation, and I conclude that the future of the coming era is the use of the fractional calculus operator. So I hope you can understand the utility of the of functions and utility of the connection between the fractional calculus and the spatial functions. So if any kind of question, then most welcome.
Okay, thank you very much, Professor Praveen, for your excellent presentation. Now, there is some questions.
Yeah, please.
Please. No questions? Okay, thank you very much, Professor Praveen, again. And
it's my pleasure, and I can say that if anyone who is want to start the working in the field of the fractional calculus, then I am open to collaboration. You can note down my email. You can just write to me on this email, goel.praveen2011@gmail.com. So you just write to me. I can provide you the study material, as well as I am happy to collaborate with the new members of around the globe. And I am once again very thankful to the organizers to give me opportunity to present my work via this platform. Thank you very much.
Okay, thank you very much.
Thank you, Mauricio. Thank you a lot, Professor Praveen Agarwal, for your amazing talk.